We're going to have a look at the next bit of proof by induction here. We've done series. Let's have a look at matrices in this video. It should only be a short video, just a couple of examples on how proof by induction works with matrices. And it works in a very similar fashion. Proof by induction always follows the same kind of steps. We test for n equals 1, prove it's true for that. We assume it's true for n equals k, and then we look at the case of n equals k plus 1. So with matrices, it's no different. So in this question, we're going to prove by induction that for all positive integers n, that this is the case. So that this matrix is equal to this. So first step always the same, we test for n equals 1. So we're going to look at the left hand side to where n is 1, which is this, which is just simply the same, because power of 1 is just the matrix itself. And if we look at the right hand side, if we put 1 in for n, we get this, so we'll get 1. This top right element here is 1 minus 2 to the 1, so 1 minus 2. And then 2 to the 1 in the bottom right is just 2. So this is true for n equals 1. So the same kind of idea as series, you prove it's true for n equals 1 to start with. And then again, we assume that it's true for n equals k, and we must write that step in. And for n equals k, that means we replace the n with the k. We're assuming that it's true, so we assume that we replace the n with the k on this side as well. And then we look at n equals k plus 1. So for n equals k plus 1, we have the same matrix on the left, 1 minus 1, 0, 2, but this time to the k plus 1. Okay, and we want to try and prove that it's true. So this kind of thing happens where it's for k plus 1 instead of k, but we'll be using that assumption in the step above. We'll be using this assumption here. So with matrices, just like in maths, if you wanted to prove x cubed, you could write this as x squared times x. Or if you want to prove x to the 9, you could write this as x to the 8 times x. So x to the k plus 1 is going to be x to the k times x to the 1, because we add the powers with these. That's how it works. It's the same idea with our matrices. So to get the power of k plus 1, this is the same as doing the matrix to the power of k, which is good because it ties in with our assumption step, multiplied by that same matrix to the power of 1. And together, the k and the 1 would make a power of k plus 1. But what this allows us to do is it allows us to sub this in place of our power of k matrix. So by our assumption, we have this. And we just need to multiply it by this. And then remember, we should always have kind of our end goal in mind. And if it's true for n equals k plus 1, somewhere out the side you want to be thinking, if it's true for k plus 1, then the matrix I get, this one, should be the same as the top matrix where the n is replaced by k plus 1. So this is my end goal. This should give me this. So I want to have this in mind as I'm working through this, just to make sure that's what it's going to end up looking like. So when I multiply these matrices, I do the same kind of as always. I take the first row and multiply it by the first column. So 1 times 1 is 1, 0 times this is 0, and add them together. First row times the second column is 1 times minus 1, and it goes in the first row, second column. And then this will be plus, and this is 1 minus 2 to the k times 2, or I can write that as 2 outside of this, so just multiply those two terms together. We'll take the second row by the first column. Second row, first column element is here. So 0 times 1, and 2 to the k times 0. And then second row times the second column, 0 times minus 1, and 2 times 2 to the k. I'm just going to put a little dot for the multiplication there. So multiplying matrices as usual. Make sure you get your elements in the right place, and then we want to try and simplify this, and we want to try and make it look like this. So I'm quite happy with the top left because it's 1, as it should be. Quite happy with the bottom left, 0 as it should be. The bottom right element is 0 plus 2 times 2 to the k, and this 2 times 2 to the k, I can write this as 2 to the k plus 1, because I can add the powers, so that matches. The only one I've got to mess around with is this top one. So let's expand the bracket, so 2 times 1 is 2, and then 2 times minus 2 to the k is going to be minus 2 lots of 2 to the k. And you can probably see where this is going. This is fine, and this one is fine. We want to leave them. Minus 1 plus 2 gives us 1, and then again this bit here, 2 times 2 to the k is going to be 2 to the k plus 1, and my minus sign is on the outside. And we've proven it's therefore true. If it's true for n equals k, it's true for n equals k plus 1, because that's what we wanted. And so just as a summary statement, I know I switched to red, but I'll go back to black. We can say, therefore, if it is true for n equals k, that was our assumption, we've proven it is true for n equals k plus 1. And since it is true for n equals 1, it is true for all positive integers n. End of proof. And then another question on this. Remember, you can pause the video if you need to. So another question. Another question. We're going to prove by induction. Same kind of idea. So we're going to prove this. So we've got minus 2, 9, minus 1, 4 to the n this time is equal to this. So exactly the same kind of idea. First step, we always test for n equals 1. So our left hand side, really simple for matrices, because power of 1 there just gives us the same matrix. And the right hand side, we've got a little bit more to do by subbing in our n equals 1. Just make sure you give yourself plenty of space so that you don't get the elements mixed up. Make sure you've got gaps between them all. And here we'll get minus 3 times 1, 9 times 1, minus 1, 3 times 1 on this bit. So we'll get minus 3 plus 1, which is minus 2, 9, minus 1, 4. The left hand side is the right hand side. Therefore, we've proven it is true for n equals 1. Always the starting point for our proof by induction. Next bit, we assume true for n equals k. So that means our matrix at the top, minus 2, 9, minus 1, 4. We assume, it's true for n equals k, so we replace the n by k. We assume that this is equal to, and again, we replace the n by a k on this side. And then we look at n equals k plus 1. So our matrix on the left, we're trying to prove it for this, the power of k plus 1. And we'll write down what we should have in mind at the end. But first of all, the way we want to look at this is we want to split this into the power of k multiplied by the power of 1, and that will give us power of k plus 1. Obviously, we don't need to write that 1 in. And this is useful because we can then use that, we can sub in this, the assumption that we made for our proof. So this then is equal to this, because we've assumed this to be true. Multiplied by this. And we want to multiply these matrices out, and the whole way through, we want to make sure we have this original one in mind here. So we want to make the right hand side work where n is replaced by k plus 1, because we're replacing n by k plus 1 here. So that will be the following. So it's good to have it in mind. For this, I'll have minus 3 outside of k plus 1, 9 outside of k plus 1 minus outside of k plus 1 and 3 outside of k plus 1 plus 1. And that's just replacing that original right hand side, replacing the n with k plus 1, and that will prove it's true in this case. So we're going to multiply our matrices out. Again, be careful with how you multiply them. First row times first column, and give yourself plenty of room for this. So we'll have minus 2 times this, plus, and then minus 1, times the 9k. So that'll be my top left element. So give yourself plenty of space. First row times second column is 9 times this, and plus 4 times the 9k. First element times the first element, second element times the second. And then second row times first column will give me this element. So the minus k times the minus 2 plus the minus 1 times the 3k plus 1. And if you're not sure about your matrices multiplication, you really need to go back and check. And then the second row times the second column, so 9 times minus k, and then 4 times the 3k plus 1. And remember, it doesn't matter which order I write the multiplication in, but I'm always adding the elements together. And I just need to expand all this and simplify, and then make it look like this thing here. So we're going to have 6k minus 2 minus 9k on the top left, minus 27k plus 9 plus 36k on the top right, 2k minus 3k minus 1 in the bottom left, minus 9k plus 12k plus 4 in the bottom right. Simplify everything, so minus 3k minus 2, 9k plus 9, minus k minus 1, and 3k plus 4, all fully simplified. Normally with maths we'd leave it, but remember we want to get it in this form, so we just need to take out things like the factor of 9 here will give me this up here. The factor of minus 1 in this bottom one will give me this. So those two elements look pretty good. So I can take the minus outside of that to give me this. I can take the 9 outside of that to give me this. And I can take 3, I want 3k plus 1, that's the same as, there's 3k plus 3, plus the 1 will make the 3k plus 4, which is perfect. And then in the top one I want minus 3 outside of k plus 1, which would give me minus 3k minus 3, but I want minus 2, so I need to add 1 onto that, which is perfect because it ties in with the plus 1 there. So it's always good to have that in mind because it helps you kind of tweak it at the end to make sure you've got exactly what you want, and it's really nice and clear that it works for k plus 1. And therefore our final little summary statement, therefore if it is true for n equals k, we use that as our assumption, and we prove that it is true for n equals k plus 1 if that's the case. And since it is true for n equals 1, that means if it's true for k, it's true for the next one. So if it's true for 1, it's true for 2, which means if it's true for 2, it'll be true for 3, etc. So since it's true for n equals 1, it is true for all n in the positive integers, and that's the end of our proof. And that's matrices proof by induction.